The easiest way in which an FPGA can be reconfigured is called complete. In this case, the configuration bitstream containing the FPGA configuration data provides information regarding the complete chip and it configures the entire FPGA. That is why this technique is called complete. With this approach, there are no particular constraints that have to be taken into account during the reconfiguration action. Obviously, that does not mean that the designer is allowed to whatever he or she wants only because he is using a configuration technique based on a complete reconfiguration. In fact, if two different bitstreams implement two functionalities that have to work one after the other, exploiting the resources of the same chip, the designer has to take into account where to store the data between these two configurations. The simplicity, in some sense, that we are gaining while using a complete reconfiguration is coming at a cost. The main disadvantage of an approach based on complete reconfiguration technique is the overhead introduced into the computation by the reconfiguration and the fact that there is no way, while working with a single device, to hide even just a portion of this reconfiguration time. In order to cope with this situation, a partial reconfiguration approach has been proposed. Partial reconfiguration is useful for applications that require the load of different design into the same area of the device, or the flexibility to change portion of the design without having to either reset or completely reconfigure the entire device. For current FPGA devices, data is loaded on a column basis, with the smallest load unit being a configuration bitstream frame, which varies in size based on the target device. Partial reconfiguration of Virtex devices, or simply partial reconfiguration, is based on the idea that instead of resetting the device and performing a complete reconfiguration, new data is loaded to reconfigure a specific area of the device, while the rest of the device will not be touched. Using an approach based on partial reconfiguration, the basic idea is to partition the overall input system in a set of functionality, F1, F2, F4, as it is in our example, where different functionality has been represented by resources colored using different colors, able to produce set of bitstream, B1, B2, B4, that are not used to reconfigure the entire system, but just a known portion of it. In our example, we can observe the partial reconfiguration of just one of the four functionalities, expressed by the changing from green to purple. Obviously, within this context, we are also looking for a sort of bootstrap bitstream, which is a complete bitstream used to bootstrap our system. But this complete bitstream, the other functionalities are downloaded to reconfigure just portion of the architecture, and because of this, we may refer to this bitstream as partial reconfigurable bitstreams. Up to now, reconfiguration has been defined from the area perspective, but there is one more important factor that can be used to classify a reconfigurable approach: the location of the controller of the reconfiguration. External reconfiguration implies that an active array may be partially reconfigured by an external device, such as a personal computer, while ensuring the current operation of those active circuits that are not being changed. On the other hand, internal or embedded reconfiguration assumes that specific circuits on the array are used to control the reconfiguration of other parts of the device. In this specific context, we are going to refer to these circuits with the terms manager, but at the end of the day, this manager is the reconfiguration controller we have already defined. Within this context, it is easy to understand that an internal configuration cannot be combined to a complete reconfiguration. If the reconfiguration has to be exploited, managed by an internal component of the chip, this cannot be entirely configured. Furthermore, it's clear that this kind of reconfiguration is based, or maybe better, it extends the concept of partial reconfiguration. Once initially configured, internal or embedded reconfiguration requires an internal reconfiguration interface that can be driven by the logic configured on the array. Within this context, we are working with a reconfiguration which is taking place internally. Instead of using an external component to implement the reconfiguration, the reconfiguration controller is placed inside the FPGA itself. Starting with Xilinx Virtex 2 parts, the reconfiguration interface used in this context is the Internal Configuration Access Port, or ICAP. These devices can be configured by loading application-specific data into the configuration memory, which is segmented into frames, the smallest units of reconfiguration. The number of frames and the bits per frame are different from the different devices of Xilinx FPGA families. The number of frames is proportional to the CLB width of the device. We can now introduce the concept of static reconfiguration. Static means that while the reconfiguration process is taking place, the system is all focused on it and no other computations are taking place. Within this context, it's quite easy to understand that a complete reconfiguration is not only external, but also static. If the entire device has to be configured, we need to have an external controller to take care of it. And obviously, we cannot have anything else happening but the reconfiguration process. This is quite easy to be understood in the complete scenario, but it is something that may happen also in the partial one, as it was happening in the soccer case. While the reconfiguration of a portion of the system is taking place, the other elements cannot continue the execution of their tasks. As we can see from this figure, in our FPGA we have 4 functionalities represented by the 4 different colors. While 2 functionalities are working, the manager will take care, as we know, of the reconfiguration of the third one. Now, within this context, we cannot allow the partial reconfiguration of the third functionality to take place unless the other 2 are not going to continue with their executions. Once they have been placed on hold, we can then configure the interested functionality with a new one. At this point, once the partial reconfiguration of the new functionality has been completed, we can then proceed in allowing the other 2 functionality to continue their execution. Which is exactly the scenario presented in this figure. This scenario is quite interesting because it's introducing some benefits with respect to the complete reconfiguration case. The reconfiguration overhead introduced by the complete reconfiguration is quite high, while here it depends only to the dimension of the reconfigurable region, which is meant to be reconfigured. Therefore, we can play with this information to try to design a system which will be able to leverage on this. Still, because of the static scenario, we can try to reduce the reconfiguration time, but we cannot try to hide it, which is exactly why we are going to introduce a dynamic reconfiguration. With such a scenario, the reconfiguration time of a portion of the FPGA is hidden by the computation of the remaining part. In order to be able to hide the reconfiguration time, it is not only necessary to partition the FPGA into a reconfigurable region to obtain the ability to compute partial reconfiguration bitstream. But it is also necessary to guarantee that the reconfiguration is not going to imply a stall in the computation of the not involved logic of the device. Such a scenario brings to the definition of dynamic partial reconfiguration. Within this context, we can define dynamic partial reconfiguration as the ability of a system to configure just certain areas of the device, while other areas remain operational and unaffected by the reprogramming, except during some inter-design communication.